All right. So we had quiz and FRQ last class. We just reviewed those. We're going to go to notes, and then there's an exit ticket. It's built into my notes. So let's go into that now. Go ahead and put your stuff away for everything except for what you need in order to take notes. And let's title these rotational kinetic energy. Okay, so we're still in rotation, of course, but now we're going to look at kinetic energy. And let me title my notes. Rotational kinetic energy. So I'm just going to add to this: anytime an object spins, it has kinetic energy. So anytime and I'm going to abbreviate. So kinetic energy, we had just a K. For rotational kinetic energy, I'm going to use a K, and then for a subscript, I'm going to put ROT, K-ROT. That's rotational kinetic energy. All right, that'll be our abbreviation. That'll be the way that we signify it in our equations. All right. Now, this is what's really cool is this is pretty simple as long as we take the notes and listen and practice it compared to what we've been doing. So what have we been doing? All right, well, we had K is equal to 1/2 mv squared. Remember when life was easy and that was kinetic energy? Well, the good thing is life is still beautiful. Life is still easy because we're going to convert this and say that K-ROT is equal to 1/2 I omega squared. Mass becomes rotational inertia. Linear velocity becomes rotational velocity squared. So this is simply just another form of energy that an object can have as long as it's rotating. If it's got rotation, it's got rotational energy because it's moving. Now, it can be moving linearly and rotating, or one or the other, but if it's rotating, it's got kinetic energy, rotational kinetic energy. All right, so let's look at an example. I'm going to scroll this up. Since there's not much there, I should be able to scroll this up pretty far, at least to there. And let's do this example. All right, what if I have a ramp? All right, I got a ramp and I got a ball on the ramp. There's my ball. And then that ball is going to eventually go to the bottom. So let me give it a different color at the bottom. So that's the ball when it gets to the bottom. And then let's say that this ramp, let's make it 8 meters tall. All right, and the ball's just sitting there at the top. It's waiting for someone to nudge it, to push it, for it to start rolling, okay? The race hasn't started yet, so it's just chill at the top. So let's just say the energy at the top, and I'm just gonna do ET for energy at the top. It's gonna be equal to our gravitational potential, right? Because that's all, it has height, but it's not moving. And we can remember that that is calculated as mgh, mass gravity height. Now this ball, as it goes to the bottom, it's going to roll, right? That's what happens with balls on ramps, right? You roll them down the ramp. So when it gets to the bottom, let me change my color so that it stays together. Energy at the bottom, I'm putting that as EB, would then be equal to, well, it's moving linearly, right? It's still moving from the left to the right. So we're going to have some kinetic energy. And it's rotating, so we're going to have K-ROT, kinetic rotational energy. I'm not trying to blow any minds yet. I'm just trying to say, hey, you know, it's up at the top, it's sitting still, it's chill, gravitational potential, right? It's off the ground, not moving, all gravitational potential. The ball is going to roll down the hill. It is moving from left to right, so it has linear motion. So that means it's got kinetic energy. It has a velocity. It's also rotating, so it's got rotational kinetic energy as well. So our total energy is divided between those two. So if we were to have a question that was dealing with this, let me use a slightly different color. What if we said, the question was written as a sphere. If I knew how to spell it would help. A sphere of mass 4 kilograms and radius of what, 1 meter? Yeah, 1 meter, rolls down a 8-meter hill without slipping. What is its speed at the bottom? Now I'm going to add in a word. What is its linear speed? Okay, let's get some things that we know from this. All right, it said a sphere, so I'm going to circle sphere. And I'm going to say that for a sphere, I equals 2/5 mr squared. And see, it's rolling. So I'm going to mark, let's see, rolling without slipping. I'm going to put in my notes that omega is equal to V over R. That's just some things that I need to have kind of in my toolbox as I'm doing this question, because I know it's going to have rotation. And part of that formula, I've got the omega, and I need linear velocity. For my questions asked me about linear velocity. So I've kind of got that in my notes off to the side. So let's put this equation together real quick. I'm going to scroll this just up enough to where we can still see this. Hopefully that's enough room for me to work this problem. All right. If the energy at the top is equal to the energy at the bottom, no friction, no magic, no extraterrestrials taking away our energy, right? No batteries in the sphere, no rocket powered grenades, nothing like that. So we're cool. So the energy at the top is equal to energy at the bottom. Energy at the top comes from mgh, and our energy at the bottom we have from our diagram is K plus K rod. All right. And then if we wanted to, let's see how I wrote that. I'm going to fix that just a little bit. I don't like doing mgh and then, so if we just say UG at the top is equal to K plus K rod at the bottom. I like that better. UG is mgh. K is 1/2 mv squared, and K rod is 1/2 times I times omega squared. All right, that's cool. See if we can clean this up a little bit. mgh is equal to 1/2 mv squared plus 1/2. What did we say I was?
2/5 mr squared.
Yeah, let's put that in there. 2/5 times m. Ooh, that's a funky m. M times r squared. And then we said omega was what? V over r? I think so.
Yeah.
Okay, cool. Let's do V over R. And then that's being squared because the formula says to square it, right? I'm not doing anything trickery there. But I can start to clean up the equation a little bit then, because this R, because it's squared on the bottom, this R at the bottom there cancels out that R squared, doesn't it? And then the 2 from that half would take out that 2 from the top of that one. So I can, that sort of clean things up a little bit. Let's write the next sentence of the math problems with mgh on the left is equal to 1/2 mv squared plus, let's see, I would have 1/2 times the 2/5. The 2's cancel out. I'm left with 1/5, right? So I'd have 1/5. The m is still there, and then the v squared is still there. Well, didn't that clean up nicely? Look at us. All right, mgh.
But what happened to the R?
All right, so yeah, look, see in red, how I slashed them out because the R square is being multiplied by the V over R that's also squared. So let me mark it again in red. This R with its square takes care of that R square. They cancel each other out because what you'd have is R squared times V square over R square, and the R squares cancel out when you do the math there. I promise it does. How about that? What's 1/2 plus 1/5?
7/10.
It is 7/10. Let's flexing our math on a Friday. 7/10 mv squared. Now they told us we wanted to calculate this for velocity, correct? All right, so we need to solve this for velocity. At this, can't I cancel my masses out? That's kind of the next easy thing to do. So let's cancel the masses out. And then how do I get the 7/10 to the other side? What would that look like?
10/7 on the other side.
Exactly right. If I multiply both sides by 10 and then divide both sides by 7, it gets me there. I feel like the lines are really small, so I'm going to skip a space and I'm going to say 10/7 times G times H equals V squared. And then if I square root that, 10 divided by 7 times G times H, that equals velocity. Well, we want an actual number. All right, so let's do the actual math. Square root of 10/7 times 10, because gravity's 10, times 8, because that was our height from our picture. That 8 comes from the picture. Don't lose that, equals the velocity. So let's do that. I got my calculator here. I've got 10 divided by 7 equals times 10 equals times 8 equals, and I want the square root of that mess is, I get 10.69, 10.69. 10.69 meters per second equals the velocity. Now, this looks like it's super long, but that's because I did one line for every little step along the way, because I wanted you to be able to see it and have reference to it. But most of you guys are pretty gifted in math and can combine steps in each line. And if you can, that's great. But for the others of us that like to see each step along the way, you've got it right here. Okay. Now, one thing I want to ask you, now that you've gotten all this written down, you're like, cool, I've got this. This is easy. What if the ball didn't rotate and it just slid down the slope? If it had no rotation and there was no because friction is what would cause it to rotate. So let's say that this is an icy ramp and we set the ball down and it just slid down. There's nothing to cause the rotation. Would K not be 0? Okay, right. It would be, but I'm not going to tell the rest of them that yet. Okay. Now, let me ask you this. Would the velocity at the bottom be bigger or smaller if the ball does not rotate?
It would still be the same.
It'd probably be bigger, I think.
All right. I've got same. I've got bigger. Anybody for slower?
Actually, it would be slower.
All right. I've got slower and same. Do I have anybody say that it's going to be bigger then? I want to know if I've got somebody on everything or not. Anybody say the velocity is going to get bigger if it slides? All right, let's try it. Let's look at it, because I'd love to tell you the answer, but I think if we work it, it's going to make more sense. Now, if it does not rotate, we're still going to say, how do we start this? The energy at the top is equal to energy at the bottom. And let's just call this one no rotation. All right, energy at the top was UG. If it doesn't rotate, what energy am I going to have at the bottom?
Kinetic.
Just kinetic, right?
So
Yeah.
wouldn't this be like the stuff we already did?
Let's see. Let's work it, because that's going to prove it, right? Where you have MGH is equal to 1/2 mv squared, right? And the first thing I would want to do here is say those masses cancel. I don't even care about the mass. Sorry for any mass fans out there. I don't care about them. The next thing I want to do is multiply both sides by 2 to get rid of the half. So I would say 2gh is equal to v squared. And then if I square rooted it, I would say square root of 2gh is equal to v. Now let's plug in some numbers since we have them. We'd have the square root of 2 times 10 times 8 is equal to velocity.
It would be bigger probably.
Yeah, now we see the numbers. Okay, yeah, you're right. 2 times 10 times 8 equals 160. I need the square root of 160, which gives me 12.65. 12.65 meters per second equals the velocity. Check it. Because it didn't rotate, it's going faster, and that is not what we would naturally think of. We're like, man, if it's rolling, it's gonna be going fast. Yeah, but you're using some energy to get that rotation. And I'm asking just about the linear velocity. If we want the fastest linear velocity, we need all the energy to be put into linear velocity and none of it to go to rotation. If we put something into rotation, the more we put into rotation, the less we have for linear. Does that make sense? I hope at least through the example we can see it, because I've got a really cool example to show next. All right, this gets us into what would have been the exit ticket. All right, so I'm gonna shrink this in, clear the screen, and then I'm gonna show you basically what the exit ticket was trying to show. So let's shrink this in. It's like I got a little spare number down there. Delete that too. All right, let's zoom this back in. All right, I'm going to draw 4 examples, or 4, we're going to erase 4 things. All right, we've got, I need 4 ramps. All these ramps are the same size, even though they don't look like I know how to draw 4 ramps the same size. Take my word for them. It's just your perspective. Just kidding, it's my inability to draw. All right, in the first ramp, I'm going to put a block. The next one, I'm going to put a ring. The next one, put a disc. The next one, a sphere, like a 3-dimensional sphere. All right, so I'm trying to show like rounded edges. All right, so we have a block. Yes, sir.
What did you say the third one from the left was?
Oh, I'm about to title them, so you're about to see it. So I've got block. This is a block, and it has no friction. All right, this is a ring, and this one has no slipping. All right, this is a disc, and this has no slipping. You know what I mean by slipping? Like it's not going to peel out. It's not going to rotate without rotating itself forward. And this one is a sphere, also with no slipping.
Mr. Watley,
Yes,
what is the F again in the first diagram?
friction.
Okay.
Yeah, my little scripty F has been friction, but I'll go ahead and spell it out there. All right, now.
Mr. Walton,
Yes, sir.
are we gonna have any examples ever with slipping?
No.
Okay.
Because there's not going to be an easy way to factor for it. So this is just saying, hey, they're going to be able to rotate without slipping. And like in order for them to rotate, they have to have friction. And where the block, we're going to say, okay, the block has no friction. Nothing's preventing it from sliding. The ones rotating without friction, they won't rotate. They'll just slide. And we're saying, okay, they're not sliding. They have just enough friction to allowing them to rotate and progress down the hill. It's kind of an unnecessary specification, but I want you to at least be used to seeing that specification. So if you get to a test that says that, you're not like, well, hold up. Have we been doing stuff with slipping all this time and now you're throwing this at me? It's like, no. It's always going to be no slipping. Okay. Now in this is going to be a race.
Mr. Watley,
Yes, sir.
I don't think I understand slipping.
Have you ever stood on ice?
Yeah.
All right. You ever fall because you slipped on the ice?
Yep.
That's slipping. All right. Think of have you ever been in a car that was trying to drive on ice and they hit the gas and their tires just spun, but they didn't move?
No. But sure, why not? Let's go.
There you go. Sure. Why not? So that's it. Let's imagine you get in your car and it's icy out and you hit the gas and you don't move and the tires just spin. That's slipping. So what I'm saying is there's no slipping. If they rotate, they're moving forward. They're not just slipping and spinning in place.
Okay. 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 I see that.
Perfect. See, we got this. Now, who wins the race? Who gets to the bottom first?
Well,
Which one?
I assume the block, but I haven't actually thought about it yet. So.
All right. So I got a vote. I got one vote for the block. Anybody else?
I think the block too.
The block. Anybody else? I mean, it's an odd. I've got a ball on a hill, and you're telling me that a square block is going to get to the bottom before a ball, and no one's voting for the sphere.
Well, I've been betrayed by that kind of thought before, so
I
I'm
know,
going
right?
block this time.
All right. First, I want to tell you you're absolutely right, but I want to show you how it's right because, yeah, absolutely. You feel like the right answer should be the ball, but that's because the block is sitting up on the hill, not moving because it's got friction. And I said, in this case, there's no friction. So when we're looking at the block, we're going to say all of the energy, they all start with the same energy because all the masses here are the same. All right. So they all have the same mass. Gravity treats them all the same. They're all at the same height. So they all have the same potential energy, right? As they go down, the ring, the disc, and the sphere will take some of that potential energy and put it into K-rod. But the block is going to take all that potential energy and put it into kinetic. So if you can put it all into kinetic, you know you're going to have the highest velocity because you've taken all your available energy and put it into linear velocity. Let's look at it. Let's see. Do we want to do each one of these or do we want to do just a little bit of these?
I have a question though. Why is it that only if it goes into kinetic it's linear? Because technically couldn't rotational kinetic the omega also be converted to linear?
Some of it is, but if we go back to the previous, I can't go back to the previous question because I've erased it all. Remember when we calculated it when it was no rotation and we got a larger value than when we had rotation? Look back at that. So yes, the rotation does give you some linear motion, but you're not going to get as much linear velocity because you have the rotation. And that's what we were seeing with that previous example.
Mr. Watley,
Yes.
I feel like it all has to do with the fraction, right? Because when because you make it a reciprocal, that's why it feels backwards. Like when you flip it, the velocity becomes greater because of the reciprocal.
Let's summarize just a couple of these at least, and it'll show exactly what you're saying. And it'll help those that are still kind of looking at this skeptically. We can say, okay, for the block, we're going to have energy at the top is equal to energy at the bottom, right? So if we say mgh is equal to 1/2 mv squared, okay, for the ring, we're going to say mgh is equal to 1/2 mv squared plus, now this is a ring, so the ring ring is just mr squared, right? Don't let me go wrong on this. So it'll be 1/2 times mr squared times omega squared. Isn't that right? And then if we looked at the disk, I'm going to scroll this up just a little bit so I can write on my pad.
A ring isn't 1/2.
No, the half is part of the formula.
Okay, yeah, that makes sense.
That's why in the parentheses, I just put mr squared. You'll see it when we get to the disk. It'll kind of make a little bit more sense. Look at this one. So we have mgh is equal to 1/2 mv squared plus, you still have the half, because that's the formula, right? 1/2 I. In this case, I is 1/2 mr squared times omega squared. And then if I put the sphere in here, just below it, we would have mgh is equal to 1/2 mv squared plus 1/2 times the 2/5, right? mr squared times omega squared. All right, since there's no friction and the block does not rotate, all of its energy is linear kinetic at the bottom, and that's going to make this one the fastest because all of it is going to kinetic energy. For the ring, the disk, and the sphere, some of the energy is used for the rotation, and it's going to be less. The object with the largest rotational inertia has the largest kinetic the largest k-rod. The more k-rod an object has, the less kinetic energy it has. So if we were to rank the others, we would say, okay, that's my largest is the block. Let's see, then the sphere would be greater than the velocity. Let's see, velocity of the sphere be greater than the velocity of the disk. Is greater than the velocity of the ring. Because the largest rotational inertia has the largest k-rod. All right, so this example, I'm gonna scroll back up where you can see all the pictures. This example, this is what was in the what was that? Exit ticket. All right, so we got through the quiz pretty decently. We're talking just about rotational kinetic energy today and finished with this example of just seeing how it really affects things, realizing that energy is constant through a system. If you can calculate it any minute in time, it's true for total energy. But instead of just talking about spring potential, gravitational potential, and kinetic, now we're adding in rotational kinetic, which is simply 1/2 I omega squared. And for the I, replace it with whatever the rotational inertia is for that particular object using your notes. Go back and see what that rotational inertia is for that object. All right, let me stop the share.